In this lesson, we'll go over the basics of specific heat capacity and thermal capacity, and then we'll look at some worked examples applying these concepts. Okay, the two objectives that we have is to define specific heat capacity and thermal capacity, and to solve problems involving specific heat capacity and thermal capacity. The reason that we need this concept is because we want some way to relate the concept of heat energy to the concept of temperature, because temperature is measurable, whereas heat energy is not yet clearly measurable. And so we want to be able to relate the measurements that we make of the temperature of an object to the amount of heat energy that's been transferred into or out of the object. And then we're going to apply that concept in a number of problems. So the first idea is the thermal capacity. And the thermal capacity, which is given the symbol capital C of an object, is the amount of heat required to raise its temperature by 1 Kelvin. And so we can write this in the form of an equation. Q is equal to C times delta T. So the amount of heat required to change an object's temperature by an amount delta T is equal to the thermal capacity times the change in temperature. So Q is the heat that we've added, C is the thermal capacity, and delta T is the change in temperature as a result of adding that heat. And so what this equation basically says is that if we have an object with a small thermal capacity, then it only takes a little bit of heat to raise the temperature by some amount. Whereas if we have an object with a greater thermal capacity, then it takes more heat to raise the object by the same amount of Kelvin, by the same change, to achieve the same change in temperature. So, for example, it takes more energy to heat up a 100 kilogram block of iron by 10 degrees than it takes to heat up a 0.01 kilogram block of iron by 10 degrees. And so we can say that the more massive block has a greater thermal capacity. The thermal capacity is useful, but it's more useful to define something called the specific heat capacity. And so this is the heat required to raise the temperature of 1 kilogram of a substance by 1 Kelvin. So this basically allows us to compare different types of substances, to compare the changes in temperature that we can achieve with a certain given amount of heat applied. And so our equation that relates these concepts now is Q is equal to mc times delta T. So m is the mass of the object, c is the object's specific heat capacity, and delta T is the change in temperature when we apply a certain amount of heat, Q. And so if we have a 1 kilogram, say, of water, which has a very high specific heat capacity, then it'll take a lot of heat to achieve a change in temperature of 1 degree. Whereas if we have a kilogram of lead, which has a low specific heat capacity, then it'll require a larger amount of heat to achieve the same change in temperature. So Q is the heat that we've added, m is the mass of the object, and C is the specific heat capacity in joules per kilogram per Kelvin. So C, the specific heat capacity, is the number of joules that we would need to heat up 1 kilogram of a substance by 1 degree Kelvin. And C depends on the type of substance that we have. So iron has a specific heat capacity, lead has a different specific heat capacity, water has a different one, air has a different one. And so this specific heat capacity allows us to compare the way that or the amount of heat required to raise different substances by the same temperature change. So for example, well, in fact, actually, let's go back to the example of the iron. So the 100 kilograms of iron and the 0.01 kilograms of iron, they have the same specific heat capacity. However, as we can see here, the amount of heat that we need to add for the 100 kilograms of iron is going to be larger because M also features in this equation. So the specific heat capacity just allows us to define in more general terms how different substances respond to heating. So for example, if we raise the temperature of a kilogram of water by 10 Kelvin, that will take more heat than raising a kilogram of lead by 10 Kelvin. Going the other way, if we allow water to cool by 10 degrees, it will release more heat than if we allow the same mass of lead to cool by 10 degrees. And we can say therefore that water has a greater specific heat capacity than lead. And what we'll do now is we'll go over a few worked examples applying these concepts, and then in class we will discuss the ideas further. Okay, in our first example, we're asked how much heat is needed to raise the temperature of a 20 kilogram iron vat from 10 degrees Celsius to 90 degrees Celsius. Okay, with all of these questions, we're going to be making use of this equation, Q equals mc delta T. And in this case, we're asked to find how much heat is needed to raise the temperature from 10 to 90, so that's a change of 80 degrees. We're given the mass and we're given the specific heat capacity. So this is just a straightforward application of this equation. It's just to get the hang of it. So the mass is 20. The specific heat capacity is 450. And the change in temperature is the final minus the initial, 90 minus 10, which is 80. And so our heat required is going to be 20 times 450 times 80, which is 7.2 times 10 to the 5 joules. Okay, and just double check our significant figures. It should be 2 because 20 and 10 and 90 are all to 2 significant figures. Okay, next example. When a car brakes, 112,500 joules of thermal energy is generated in the brake drums. The mass of the brake drums is 28 kilograms and their specific heat capacity is 460.5. Calculate the change in their temperature. Okay, so here we have, again, we're going to use Q equals mc delta T. And in this case, we know that Q equals 112,500 joules. We know that M is equal to 28. And we know that C is equal to 460.5. Joules per kilogram per Kelvin. And so we just rearrange this equation to get the change in temperature. Delta T is going to be equal to Q over mc, which is 112,500 divided by 28 times 460.5, which is equal to 8.72. How many significant figures do we want? We want just 2, so let's just get rid of that. 8.7 Kelvin. So we're going to get a change in temperature of 8.7 Kelvin when we apply that much heat. The specific heat capacity of copper is 385 joules per kilogram per Kelvin. Calculate the increase in temperature when a 0.5 kilogram block of copper is given 20 kilojoules of thermal energy. So again, the equation is Q equals mc delta T. We want to work out what the change in temperature is, and we're given that the mass is 0.50 kgs. We're given that the heat given, transferred to the copper, is 20.0 times 10 to the 3 joules. And we're told that the specific heat capacity C is 385 joules per kilogram per Kelvin. So, and we want to find out what the change in temperature is. We can just go delta T is equal to Q over mc, which is 20 times 10 to the 3 over 0.5 times 385, which is equal to 103.89. How many significant figures do we want? Just 2, because our mass was given to just 2. So let's just state this to the correct number of significant figures. So we really want 1.0 times 10 to the 2 Kelvin, or 100 Kelvin. Alright, example 4 asks us that 20.2 kilograms of water at 70 Celsius is mixed with 0.3 kilograms of water at 10 Celsius. Calculate the final temperature of the water. Okay, this is a bit more complicated because the heat lost by the hot water is going to be equal to the heat gained by the cold water. And those two things should be equal because any heat gained has to have come from the heat lost by the other one. And so we can use this to figure out what the final temperature of the water must be. So we use the same equation that the heat gained. So maybe we'll write it like that first. So Q gained is equal to Q lost. And so M1C1 delta T1 is equal to negative M2 C2 delta T2. So, in fact, maybe it'll be clearer if I say it like this. I'll just try doing this. If we say M hot, C hot, delta T hot, it's got to be equal to M cold, C cold, delta T cold. However, one of them is a gain and one of them is a loss, so we have to make one of them negative. So let's say the one that drops, that loses temperature, is going to have a negative heat. And so they're both water, so they both have the same specific heat capacity. So we can cancel that. Cancel that with that. Okay, and then the next step will be then to write in what we know. We know that the mass of hot water was 20.20 kilograms. So we have negative 0.20 times, and the final temperature is what we're trying to find out, minus the initial temperature, which is 70, must be equal to 0.30 times final minus initial again, TF, minus, the initial here was 10, and because we're dealing with changes in temperature here, it doesn't so much matter whether we work in Celsius or Kelvin. Otherwise we should work in Kelvin typically, although in this case, as I say, because it's a change, it doesn't matter. Okay, so now what we want to do is just solve this for TF. So let's get all the TFs over on one side. So what we have here is negative 0.20 TF minus, in fact it's negative 0.20 times negative 70. So negative 0.20 times negative 70 is 14. Is equal to 0.03 TF minus 3, because 3/10 of 10 is 3. Okay, so now we can move everything over to one side. So let's move all the TFs over to the right and all the numbers over to the left. So we have no, sorry, I've made a mistake here. This should be plus, because it was negative 0.2 times negative 70. Okay, so let's move all the TFs over to the right. So we have and all the numbers over to the left. So 14. So if you add 3 to both sides, we get 17 on this side, and if we add 0.2 TF to both sides, we get, there's an error here as well. It shouldn't be 0.03, it should be 0.3. So we're going to get 0.5 TF. And so TF is going to be equal to 17 over 0.5, which is 34 degrees C. Okay, so we have a 2 kilogram block of copper heated to 100 degrees, and it's placed in a half a kilogram of water at 10 degrees. Calculate the final temperature. Okay, this requires us to know the specific heat capacities of the two, because they don't cancel in this instance like they did in the previous example, because they're different. So we know from, let's just fix the size of that. And let's rub this out. Okay, so in fact let's rub it out completely. C of water is 4200 joules per kilogram per Kelvin, and C of copper, we know from the earlier example, is 385 joules per kilogram per Kelvin. Okay, and then we use the fact that Q lost by copper is equal to Q gained by water, and so we have that's MC delta T, and because it's a loss we're going to make that one negative, of Cu is equal to MC delta T of water. Okay, and plugging in the numbers, we have 2 kilograms of copper, so that's 2 times 385, which is the specific heat capacity of copper, times, oops, that's a bit messy and it looks like a negative sign, let's get rid of all that, times the final temperature minus the initial temperature. So the final temperature we don't know, TF, minus the initial temperature of the copper, which was 100, and that, in fact that should be a negative as well, because it's a loss of heat by the copper. That must be equal to MC delta T of the water. We had 0.5 kilograms times the specific heat capacity, which is 4200, times the change in temperature, which is Tf minus, and the starting temperature was 10 degrees. Okay, so there's our equation. Now once again we need to solve this for Tf, and so we'll just multiply out the brackets to begin with, and if we do that we get negative 770 Tf plus 7700. That's 770 times 100. That must be equal to 0.5 times 4200 is 2100 Tf minus 21,000. Okay, and now rearranging this, let's move all the TFs over to the right and all the numbers over to the left. We get 98,000 is equal to 2,870 TF, and so TF is equal to 98,000 over 2,870, which is equal to 34.14. How many significant figures? We only need 2, so 34 degrees C is the final temperature. Okay, you can use these as an example, as a guide for completing your own practice. And you do need to do quite a bit of practice with this just to get the hang of doing the problems. And one of the things I really want to point out about these is this negative sign up here, and keeping your signs straight when you're multiplying a negative by a negative, because that's one of the most likely sources of careless errors in these problems. Okay, we're going to do an experiment that's similar to this last example in class, and we'll do plenty more practice on this type of problem.